الآن يمكنكم المشاركة في مبادرة الأيام الرقمية تحت شعار انطلق بقوة مع جوجل، والتي يتناول فيها خبراء جوجل عناوين جديدة أسبوعيا مثل السحابيات، مهارات من جوجل، أندرويد، فلتر، ذكاء الآلة، فايربيس، ديزاين ثينكينج، مقسمة إلى دورات وورشات عمل يومية بالإضافة إلى مسابقات أسبوعية. شاهد الأيام الرقمية مباشرة على اليوتيوب وشارك رأيك وأسئلتك مع خبراء جوجل، واحصل على شهادة حضور في كل محاضرة تشترك فيها. هذا وأكثر من الأحد إلى الخميس ابتداء من الساعة 9 بتوقيت دبي عبر الرابط المبين youtube.com/gdgmina.
Hello. Hi, everyone. I'm Youssef Dhieb. I'm a Google developer expert in machine learning, and I work as an AI engineering lead at Dhieb. And in today's session, we will talk about computer vision projects, and we'll talk about different use cases and which models to use in different use cases, etc., and what type of learning you will need, and the best practices to accelerate also your computer vision data loading. So for the contents, we start with the computer vision tasks, the different tasks we have, like image classification, object detection, etc. Then we will talk about the different computer vision use cases when you have a small amount of data, or where you have a big amount of data, but it's not labeled. In the third part, we will talk about data augmentations and how you can improve your results by just augmenting your data. Then we'll talk about the data loading, how to accelerate your data loading pipelines. And in the last part, we'll talk about data-centric AI. First, let me start by giving you the Slido QR code. So we will use Slido in order to be able in order for you to be able to use the Q&A at the end of the session. So here you can see the QR code, or you can go to slido.com and to computer vision. You add the code actually CV projects so that you can join the quiz. I will give you a few seconds so that you can join on Slido. Okay, so yeah, just let's test if it's working or not. So for the first question, did you work before on computer vision or deep learning projects or not? Just to know the audience. Do you have any experience? Did you work on like small projects or personal projects, or did you work on professional projects at the company you are working at? Okay, so it's working. We have 4 people, so okay. Good. Okay. Yeah. Anyways, so today's session actually is intended for people who either worked on computer vision on a small project or did not have experience before with computer vision projects. It's mainly meant to help, for example, students at the end of their studies who want to build, for example, prototypes. If they want to start a startup or start a project and want to do a prototype. So we will discuss which model should they use, where to find these models, and according to their data or tasks, so what they should do. Okay, so let's move on. So for the first part, we'll discuss the different computer vision tasks we have. So in computer vision, we have many tasks like image classification, object detection, etc. We'll go through them one by one. So the first task is image classification. And in image classification, what we have is we have images and their labels. And the model or deep learning models here, or our algorithms, their goal is to define if this image belongs to the first class or the second class For example, if we have a data set of dogs and cats, and so the task here, the image classification task, what the model will do, it will predict if this image is a cat, an image of a cat, or an image of a dog. So this is the first task. So the output usually is depends on the number of classes. If it's only 2 classes, so the output is just one output, which will give you, it's either a cat or a dog. Otherwise, if we have like 5 classes, we will have 5 outputs at the end. Then the next task, we have the object detection. And in object detection, the difference between the object detection and image classification is that we try to find the object inside the scene, and we can have multiple objects inside the scene. So the model will give us in return a bounding box. Well, it will return the coordinates of the bounding box in the class of that bounding box. So here, for example, as you can see, it's detecting people. So for each person, it detects a bounding box and it outputs its probability first, or confidence, and it outputs its class. So if it's person or a car or a traffic light. So this is for object detection. Then the third task is semantic segmentation. And the difference here is that in semantic segmentation, we try to assign for each pixel in the image a specific class. For example, here for the cars, they have the blue color. So for each pixel belonging to the car, we assign to it the blue color or the car class. For the road here, we assign the gray color or the road class. For people, we assign for each pixel belonging to any person, we assign a value, which is the value for the class for that person. Then we have, for the next task, the pose estimation. And we try to estimate the pose of the people. And we have different key points here in the head, in the body, etc., legs and hands. Then the next, task is image restoration. And for this type of tasks, we usually use what we call generative models. And the goal here in this task is to restore images and remove noise or artifacts in the image, as you can see here. Another task in computer vision is image generation. We can also generate images of people that do not exist, and we can even modify them as we want. If we want to modify the hair color, the smile, if he or she is wearing a glass or not. So this is called image generation, and for that also we use generative models. Then the next task also we use generative models, and it's called domain adaptation or style transfer. So we transfer the style from this type to this type. For example, we can transfer the style from the winter to the spring, or from the horse to the zebra. Then another task is the object tracking, and usually it's detection tracking at the same time together. Then the last task, we have the super resolution, and the super resolution will allow us, for example, if we have a small image or a bit blurry image, to improve its resolution. And for this also we use usually generative models. So now, depending on the use case you have, so where can you find the deep learning model for this task? Let's say you want to do a classification or object detection. So what can you do, and how to find these models and where to find them? So you have 2 good sources here. The first one is TensorFlow Hub by TensorFlow by Google. And here you can find the models, and you can find examples how to run these models. And we'll look into that in a second. And you have also papers with code. So papers with code, in papers with code, you will find the state-of-the-art models for each task. It's not only computer vision, it's even for TensorFlow Hub, it's for computer vision, natural language processing, or any domain. And for papers with code, actually, you can find the paper, the research paper, so that you can read it, and you can find the different implementations on GitHub, so that you can implement the code by yourself. So I will start with the papers with code. And Let me look at it in Google. So just look for it in Google, and you click on the link, it will open up papers with code. So here you can find the trending research in the main page. Otherwise, you can go to browse state of the art. And here you will find the different tasks. For example, for computer vision, you can find the semantic segmentation, image classification, object detection, image generation, etc. You have also other domains like natural language processing, etc. So let's see the computer vision. And let's look, for example, for the object detection. Let's say we have an object detection problem and we want to implement a model. So here you can find the state-of-the-art models that are used now. And you can even look at benchmarks like the COCO dataset. So when you click on it, it will show you the different models and their scores compared to each other. So here you can find the best models. For example, you can find the mask RCN in here, the faster RCN in here, etc. And when you go to one of these models, you want to implement it or you want to read the code, you just need to click on one of them. Okay, let's go, for example, for Dino. So here you will find the PDF. It will redirect you to Arxiv so that you can read the paper in itself. Otherwise, you can find here the implementations on GitHub so that you can implement that by yourself and test the model by yourself. So when you see official, this is their official implementation. Otherwise, these are other implementations from other people, and you can see which framework they used, either PyTorch or TensorFlow. And what you need to do is just to understand the paper if you want and read it, and then go to the code and try to implement the model on your data. Otherwise, we said also that there is TensorFlow Hub. If you want something easy and very quick to test and to use, especially if you are doing a small POC that you want to prove something, so you can make it work, I mean, in a few minutes or hours. So let's go, for example, look for TensorFlow Hub. So for TensorFlow Hub, you will find the different models, either for image, for text, for video or audio, and you will find also different format. TF.js is for web browsers. TF-Lite is for embedded systems or mobile devices. And you can look at the images here. Let's look, for example, for images and look for, let's say, object detection. So let me remove all the other ones and give the object detection. And here you can choose the TensorFlow version you're looking for. Let's say we want to work with TensorFlow 2. So here you will find the different models existent in TF-Hub, and it's very easy to use. Let me show you an example here in the main page. For example, for the object detection here, let's say you want to use faster RCNN. So it will open up the page for the model for the faster RCNN with Inception ResNet v2. And so it says that the format is TensorFlow 2.0. So it gives you an idea about the model, etc., the output. And here you will find an example how to use it. So in order to load the model, you just need to use TensorFlow Hub package. So you use hub.load and you put the link to the model. And you give it the tensor image, and it will give you back the IDs of the objects detected in their coordinates. So here it explains all the outputs, etc., and how to work with it. And if you want to quickly test it, you can just go to Open Colab Notebook. So it will open a Google Colab, and a Google Colab is like a Jupyter notebook, but it's hosted by Google. And you will have access to a free GPU there and free CPU, so that you can test your code directly there. And here they are providing the code to work with a faster RCNN. So what you need to do is just to run your code, just run your code, and you can test here with the images you want. So loading an image here. So you can select one of these images, or you can load your own image and just run the code, and it will give you the results. So this way, if you have a prototype where you want to use object detection, and especially if there is, let's say you want to use object detection of people, for example. And so the model here is already trained on that. You don't have to even to train the model. So you, from the outputs, you will just filter and get the persons detected and use that into your application or your proof of concept. Okay, so going back to the presentation. Okay, so now that we talked about the different use cases, the different actually tasks, in this part we will talk about the different use cases, especially the data use cases. If you have data, you don't have data, etc. And actually, even the idea of this talk, it came by after mentoring multiple startups at the first stages, and seeing where they were struggling when building AI models. So that's why I made this section. So because usually people get stuck when they have, for example, a small amount of data, they don't know what to do, which data to collect and how to collect it. So the different use cases we usually have is that either we have a model that exists and it's already trained on your use case, like we were seeing for the faster RCNN trained on COCO dataset. So if you are trying to train to use a model that detects persons, you can use that. The second use case, it's when the model exists and you need to train it on your own data. And here we have two cases. So either the data is totally different, and do we have a sufficient amount or not, and the data, is it labeled or not? Or the data is close to the pre-training data, and this is another case. And then the third use case is when the problem is not tackled before. And here usually it comes when you are trying to solve a scientific problem using computer vision. So here you need to create your own model or modify an existing model to work on your use case. So let's start with the first use case. So if the model exists and it's already trained on your use case, so here, for example, like the COCO dataset, it's already trained to detecting people. So what you can do, so you have either the possibility to use the Google Cloud Platform, use the Vision API. If you don't want to develop your model or you don't actually have the compute power after that to run it. So you can use the Vision API where, let's say you are building a mobile app that tries to detect people. And so what you can do is you can program your mobile app to communicate with the Google Cloud Platform. It will send the image, and the Google Cloud Platform, or the Vision API, will send back a JSON file, and it contains the persons detected and their coordinates in the image and the probability. So this is the first use case if you don't want to use your own, let's say, compute power. And the second use case, if you want to use it on the mobile, or you want to use it on your computer, etc., or on your own server, so you can use TensorFlow Hub and just use take the models from there and use them in your application. Then the second use case is when the model exists and you need to train it on your own data. So here the models, for example, for image classification, let's say we want to use image classification. We have an image classification problem. So the models, they exist. We don't have any problems with these models, but we need to train them on our own data. For example, here, let's say the data is close to the pre-training data. And here, an example is, for example, let's say that the model was trained on dogs, detecting dog breeds, and we want to create an application that detects wolf breeds. So what we can do is that we take that model, which is trained on dogs, and we just fine tune it on Wolf because the data is very close. You will not need a lot of training. And also what you can do, even you can freeze a few layers from the model and keep the last layers trainable. And you train only the last layers since the data is very close together. Otherwise, if the data is not very close, let's say, for example, the model is trained on, let's say, COCO data set, and you want to detect after that, let's say, a few categories that are not in the COCO dataset, but are usually present there, like detecting shoes, for example, in the image. So here you can also take a pre-trained model on COCO and just retrain it on your own data on the shoes. You just create a small data set. Even with small data set, in this case, it could work. Doesn't have to be like thousands of images. Then the second case also, when we don't have similar data or data is totally different, here there is also two use cases. Do we have sufficient amount of data or not? And do we have labeled data or not? And such an example is for example, the medical imaging. We cannot take a model trained on COCO dataset, for example, trained on people, on cars, etc., and try to apply it to medical images. We try to just fine tune it on medical images. So this will not work. And here we have different solutions. So let's say we have a big amount of data which is labeled. So here you will have to train your model from scratch, since you have a lot of data and it's labeled. Otherwise, if you don't have a big amount of data, maybe a big amount of data that is labeled, you can have, for example, a small amount of data that is labeled, let's say 500 images, and a lot of data that is not labeled. Let's say, for example, thousands or millions of images that are not labeled, but at least you have a lot of data here. So here we can use what we call self-supervised learning. So we teach the model to train on different tasks on this data, on the unlabeled data, just to learn the patterns of the data. So we'll try to remove, for example, some patches from the data or detect if two zones from the data are belong to the same image or not. So in this way, when we train the model this way on unlabeled data, it will learn a few features from the image, and then we can just retrain it later on the few labeled data we have. And this is actually one of the biggest trends now in computer vision. Then we have the third use case, and here when our problem was not tackled before, and we need to create a new model or modify an existing model. For example, let's say we need to do like semantic segmentation in 3D, or actually there are some models for semantic segmentations, but let's say instance segmentation in 3D, and you want to use, for example, mask RCNN for that, because it's providing good results. So here you have to modify that model by yourself and converting it to 3D in itself, and then training it on your data. So these are the different use cases, and yeah, and here so you will have to use TensorFlow or JAX or PyTorch or any framework to implement it by yourself or modify it. Yeah. So next we have the data augmentation and data loading. So one way also to improve your results, to improve the accuracy of your model, so either by increasing the amount of data you have, or taking the data you have and try to increase its amount by doing some data augmentations. So how does data augmentation work? We take, for example, each image, we apply different transformations. We can apply rotation or flip, etc., or translation, and so that the model can see a lot of images and a lot of different images that are coming from the same instance. And this will actually help a lot the model to become even more robust to the data. So these are different types of data augmentation. So we have the flip, and we have the horizontal flip on the center, and the vertical flip on the right. We have also the rotation. It's either by 90 degrees, or you can choose, for example, when you're training your model, you can choose like a 30, 20, etc. You can make it variable, the number of degrees for better results. You have also the zoom or here. We have also the cropping, we can crop, and we have the translation, but usually for convolutional neural networks, translation doesn't have a lot. And we have also other types of augmentation on the images, like for example, the brightness and contrast. And here, actually, there is a good library called Albumentations that you can use for your data augmentation. And why use Albumentations? Because coding these types of augmentation can slow a little bit your code, and you will have to implement like something very high performance. And with Albumentations, all the algorithms are already very fast, and they have a lot of data augmentation algorithms. So for example, here you can see the RGB shift, hue saturation value, etc., the random brightness. So all of these are only on the colors. They have also the flip, the rotation, all of that, and they are very, very fast when you implement that in your code. And the good thing with argumentations is that you can use it with, you can use the images with their labels, and it will convert automatically the labels. For example, here, when we flip the image, and we do some cropping and resizing, the bounding box will stay always around the objects. So they will do automatically that for you, so that you don't have to compute that by yourself. For segmentations also with masks, they will do the same. So I highly recommend using augmentations in for data augmentation. So because the data augmentation will increase also a lot the accuracy of your model if you're not using it. Then the next part is the data loading. So the data augmentation is actually for increasing the accuracy and robustness of the model. But the data loading here, you should pay attention to that, because it will increase the speed of the training actually. Because if you are not implementing an efficient pipeline for loading the data, you will face many problems in terms of memory and in terms of speed. So you can, for example, profile. I will show some profiling with TensorBoard on the data loading. And here you can see, so here you can see the training steps. And at first, so we have the scheduled execution by the CPU. And then we have the heavy lifting done on the GPU. And all the time between, it's waiting for the data to load. So here you are waiting, like wasting a lot of time just by waiting for the data each time after training each epoch to load the data, transform it, and then give it back to the model. And you are doing that in a way that wastes a lot of time. Sometimes you can think that it's from the model, but many times it usually comes from data loading itself or data transformation. And for that, you can use tf.data if you're using TensorFlow. And so that you don't have to do the transformations in Python, etc. So you can use tf.data.dataset and then use, for example, to shuffle your images, you can say use the shuffle method, or you can use the map method to apply any transformation. To convert them into batches, you can use the batch method. You can also use the prefetch, so that when you are training already the model on some data, it will prefetch the next batch of data or the next data from the disk or from the RAM while the model is training on the current data. And here, by just applying tf.data, you can actually double the speed of the data loading. Then, so the last part, which is the data-centric AI. And this part is actually quite important, and it's also one of the biggest trend now in computer vision. So I took this part from Dr. Andrew Ng's talk on YouTube. I advise that you take a look at the whole talk. It's quite informative. So for the AI systems that we are building now, so they're composed of two things: the code, which is the model and the algorithm, and the data. And what we have been doing the last years is that we have a data set and we want to obtain very good results on that data or on the test data. And what we do, we iterate on the code or on the model. So we try first model, then we try to fine tune it. We try to change the hyperparameters. We try to increase the number of training epochs, change the learning rate, etc., so that we can increase the accuracy of the model on the specific data or on the test set. While actually we should not have done this. And here a good example that he usually gives is that when you're cooking, for example, cooking a meal, so 20% of it is just the cooking, and 80% is from the meal is coming from the high quality ingredients. So if you are, even if you are the best chef and you are cooking a meal with very bad ingredients, you will get a very bad meal at the end. And here is the same thing with the data and in deep learning. So if you have high quality data, even if you use let's say an old model, let's say you use a ResNet 50 or ResNet 18 on your data, if you are doing classification and you have high quality data, you will get better results than using the state of the art models with very bad quality data. So here, and also it will use less effort actually to fix the data and provide clean data than try to iterate on the model and try to implement state-of-the-art models, etc., and train multiple times. And we can get high-quality data first by having a consistency in labeling. And so here there is this is an example of labeling. So this is a picture where we want to label the dogs. And the labeling instructions given to the labelers are used by bounding boxes to indicate the positions of the dogs. So we have different cases here. So we can, the first labeler could give us this labeling. So this is the bounding box indicating the position of the dogs. So this is first case. The second labeler could give us this label, and which is actually better because here you don't have free space in here like with the first labeler. Then we have the third labeler who could give us this label in here. So he will give us a bounding box for each dog. And the fourth labeler will give us these bounding boxes. And the difference here is that for the black dog, it will continue with the bounding box until the end of the tail, and it will take into account this occlusion, while this one will not. So, and all the four of these labelers, they are following the same labeling instruction. So here, having a very consistent labeling is important, because if we have a data set where we have these four types of labeling, we cannot even measure a good a test accuracy or a test precision, because let's say we have a label in the test set like this one, and the model outputs a label like this one. So we'll have an error here, and we will have a drop in precision. Well, it's not true. So we will have to first have very consistent labels, and they should all label the data in the same manner. And we should have, like, especially for the test set, we should have a very clean and correct labeling. And for the data-centric AI, so there are two ways in the workflows. So we were usually, before we were doing model-centric AI, as I said. So we take the data, we collect the data, and we try to train a model on that data and try to find the best results. Then each time we will try to iterate over on the model, and we will try to change the hyperparameters, change the size of the model, change the scheduling of the learning rate, etc., and all these different techniques just to improve the accuracy of the model. While the best thing to do is to use the data-centric approach. And so here you will keep the same model. You can take a ResNet 50 or a ResNet 18. It depends on your image sizes and the complexity of your problem. So you just take a normal model that's not sophisticated or complicated. You can easily implement, and you will let me fix it, and you try just to improve your data each time and increase each time the accuracy of the model by just increasing the quality of your data. And while the model-centric approach usually could give you like an accuracy, like an improvement in accuracy of let's say 1%, 2%, 5%, the data-centric could give you 10 to 20% better accuracy. So for the workflow for the data-centric, so the first thing is when you collect your data, so you should ask the question, how do I define and collect my data? And then when you start training the model, you should ask the question, how do I modify the data to improve the model performance? And then when you deploy the model, you should ask the model, ask yourself, what data do I need to track or concept or the data drift? And here, actually, so when deploying, you should check the failure cases or where your model failed and check this data, correct it, and add it to your own data. So a few tips at the end for the data-centric AI development. So the tip number one, you should make the labels consistent, as we showed in the example of the dogs. You should also use multiple labelers to spot the inconsistencies, because if you have only one labeler, he will use the same, or she will use the same type of labeling, and you will not be aware of any inconsistencies after that. So the best thing is to use multiple labelers, and they do not see each other as labeling. And after that, you take all of these labeling and compare the different types of labeling and what they did. Then the third tip is that you should clarify the labeling instructions for the labelers, and this is done by when you track down the ambiguous examples. When you train your model, for example, and find that it failed in a few images, so you need to analyze that and give them the feedback on how they should improve their labeling, or how to be consistent on that stuff exactly. And the tip number four is that you should toss out noisy examples, and more data is not always better. So let's say you have a data set of, let's say, 10,000 images. It would be, and it has like, let's say, of 10% noisy data. It would be better to correct that 10% of noisy data, and it will give you better results than adding 5,000 more images. So just by fixing the small amount of data you have that is noisy will improve dramatically the accuracy. And then the last tip is to use error analysis to focus on a subset of data to improve. So you should check the failure cases and check which subset of data the model is failing at, and you should review it and relabel it if necessary. So by that we are done with the presentation. Yeah, so let me go through the questions. Yeah, so you can join Slido using this QR code, or you just go to slido.com and add the code CV projects, and you will be able to use the Q&A here if you have any questions. So the first question is from Amar. Hello, I want to learn data analysis. Yes, but actually this talk is more about computer vision, more than data science and data analysis. The second question is, the pose estimation looks so cool. Can we detect body language poses with it? Yes, and there are actually a few models that do that. There are people who work on detecting body language poses with it. Okay. So the name of the course is Computer Vision Projects, Use Cases and Best Practices. Okay, so there is a question from Anonymous. Thank you. The last question, can you please elaborate on training models on non-labeled data and how that enhances the results? So for unlabeled data, you will have to use unsupervised learning. But if you want to get good results, you should actually have a small subset of data that is labeled, and the rest you need to have like a big amount of data that is not labeled. And here you will use what we call self-supervised learning. So how self-supervised learning works, we try to have to give the model a few tasks for the model to do on the unlabeled data. For example, let's say we remove some patches from the data and we ask the model to complete these patches. Or we take two regions from the image and we ask the model if these two regions belong to the same image or not. Or for example, we take the image, we divide it into 9 sections, and then we shuffle them and we tell the model to reorder these sections or these zones to in the correct way. So by doing these tasks, the model will learn a lot of features in the data, and by that we will have like a pre-trained model on that data. And after that, you just need to train your model on the small labeled data set that you have. I hope that answers your question. Do we have any other questions? Okay, another question. Hello, how to reduce the error margin for a computer vision project? Yeah, how to reduce the error margin. So it depends. So here it depends on the data in itself. You need to analyze actually the data. So one good thing to do usually is that you run some after training your model, you do an inference on your validation set and on your train set, and you should check the images that have the highest losses. And usually these images, they contain the errors. So the first few images will contain the errors in labeling, and you can check them, do your data analysis, and check why they are giving bad results. Or what you could have also, you could have an unbalanced data. You could have some categories or some classes or even some patterns in the data that are not very present, that we have only a few images from them. Or what you can also have is you can have like some biased data where for example, there are let's say you are using a model or training a model to detect dog breeds. And there are breeds that exist in the test set, but they don't exist in the training set. So here, for sure, you will have like errors in these images, and you will have that constant margin of error that will be always there if you don't fix your training data and if you don't add this pattern into your training data. When using the data-centric approach, which is the fastest way to architect your startup on microservices? Could you please develop more on that question, because it's a bit broad. I didn't get it. And for now, there are not many many tools for fixing your data for the data-centric approach. So usually you will have to build your own tools for that. you will have to build your own tools for the labeling. There are some, but for detecting, for example, specific cases or to do something that is like specific to your use case, here it can be tricky, and you will have to implement your own actually applications for that, or your own tools. For these tools, actually there are two examples that I remember of. So let me show one of these. So one of them I saw before and I liked it, which is for data labeling. It's called V7. Yeah, it's called V7 Labs. I gave it a try before. It's very good if you want to have good data labeling. They have also a free trial. You can use that. And you can even use their models there directly when you label the data. You can run them on your own data without even having to code the models. Another also tool that I like a lot, which is using self-supervised learning. It's called Lightly. So Lightly here will allow you, using self-supervised learning, will allow you to study and analyze your data. Let me show an example here. So you will be running like self-supervised learning on your data, and you will be able to detect the difference. For example, if the data is unbalanced or not. Here, if you detect, for example, from videos of the cars, you will detect that there are images that are blurry. And you can even detect, for example, the difference between your images. For example, here, these are all images in the daylight, and here are night images, or images taken in the night. So this way you can understand more your data, and you can make it balanced because we have here, for example, a lot of images that are taken in the day, and here fewer in the night. So you can take the same amount from each subset and train your model on it so that it becomes balanced. So this is also a very good tool to use. And you can also use it like use the self-supervised learning here, and so that you can output some embeddings for your data and use that after that with your own models. I hope this answers your question. Okay. You're welcome. Okay. So when using the data-centric approach, this is the first way to architect. Okay. How to reduce the error margin? We answered that. And please, more tips on adapting data to train it on various models. Could you please elaborate more on that? So here in data-centric approach, it's actually fixing the model instead of modifying the model. We don't have multiple models, so you just at first put just one model, and then you just put one model. For example, let's say ResNet 50, and each time you iterate over your data, you fix the images and you retrain again that same model. You don't change the model at all until you increase the results and you obtain very good results. After that, you can maybe use a better model when you have very clean data. Okay, we don't have any other questions. Okay, then I think we are good to go. I hope that this session has been beneficial for you and that you enjoyed the session. Thank you very much and have a nice day.